Okay. Good evening, everyone. Welcome to the May Chemaraderie. My name's Terry Humphreys, and I'm your host for this evening. Thank you very much for coming along. This is our first Chemaraderie that we've held on a Thursday. We've been trying to mix it up so that more people come on different dates, so thanks for coming. I'd like to start by acknowledging the traditional custodians of the land that we're meeting on today, the Whadjuk Noongar people, and I wish to pay my respects to their elders past, present and emerging. On to the main event for this evening. We've got Associate Professor Rafaela de Michaelis here tonight from Curtin University, speaking on atomic scale modelling of minerals and mineral fluid interfaces. I would read out the biography for her today. But you've probably seen it in the newsletters and online. One thing I must mention is the amount of prizes that she seems to be getting. Her research seems to be doing very well, getting the 2020 Young Tall Poppy Award and the Dorothy Hill Medal. So yeah, it's fantastic to see good recognition. But yeah, please welcome Rafael to the stage.
Is it there? Yes.
Yep.
It's that one.
Okay, and switch. Okay.
Is it on?
Should be.
Looks like. Okay.
Okay.
Good. Okay. Good evening, everyone. Thank you for coming, and thanks to the organizers for inviting me to give this talk. So I will start by acknowledging that we're meeting on Whadjuk Noongar Bodja, which is an amazing country, and it's a privilege to be able to live here. But originally, I come from here in northern Italy. And so this is pretty much how it looks in the 4 seasons we have there. And this has recently been awarded as, recognized as a UNESCO World Heritage Site. Now, I don't know if you know, but Italy is the country with the most UNESCO World Heritage Sites. And I come from a place that is the intersection between two. So it's a pretty, we're all very proud of that. However, if you come from up to the hills in there, you either become a winemaker, you become a wine seller, or you just move. So why am I not running a business there? I don't know. It's a question I ask myself every day. But at some point, I choose the path of science, and I went in Turin, at the University of Turin, to study chemistry. So most people wouldn't know that Turin was the first capital city of Italy, and then it was moved to Florence and eventually to Rome. And with the many wonders that are in there, there's the Royal Castle, and next to that, there's the Royal Library, which hosts a huge collection of Leonardo da Vinci's drawings, including his famous portraits. Now, what am I doing here, and what am I doing in Australia, and why? So I moved here originally for a postdoc, and then a number of opportunities came and were successful. So I'm still here, and my research is about understanding the chemistry that happens in nature and why it happens. So this is again the Leonardo da Vinci. He used to say that nature is la maestra dei maestri, the teacher of all the teachers. He says that the vast majority of the things that came up to his mind, they came through observing nature. And there are many other artists and scientists that deliberately tell that all of their inspirations came from nature. And indeed, nature is full of chemistry that is undiscovered, and that has potential applications for current and future challenges. You see here, this is a coccolith. It's an organism of a few nanometers, or micrometers, sorry. So you wouldn't see it with bare eye. And you've just seen in the movie that it's like inside these organisms, there's something that happens that synthesized this material with a perfect shape, structure, texture. So this is like science fiction for material science. So what if we were able to design and synthesize materials with the same level of accuracy that living beings do, including ourselves when we grow our bones? Now, this is the why mineral fluid interfaces, why a chemist should be interested in minerals and in the interfaces with the rest of the world. Because minerals are like a stage for chemistry to happen, and you have all sorts of processes that happen in the environment that support life, planetary evolution, and everything else. But the chemistry underpins these processes, and we know very little about it. In particular, the two areas I'm most interested in is the interactions of certain mineral surfaces with water and carbon dioxide. So in nature, this naturally happens in a variety of natural setups. It's just that we don't know how to make it happen because these environments are too complex or too extreme. It happens in space, on ocean floors. So we don't really know what happens here. We just observe it happens. And another area I'm interested in is biomineralization and mineral growth in general. Nature is able to grow stuff, materials, with a variety of, with a perfect control, like exactly that. Think about your bones, it's calcium phosphate, but they are grown exactly the way they should be by nearly everyone. So again, what's the chemistry that underpins this process? And is there something we can learn from what happens in nature to be used for a variety of applications? Now, this is I hope I have convinced you that mineral fluid interfaces are something a chemist should be interested in. Why modeling? Now, this is the typical approach that we all have when we run experiment. So we have a sample. So I didn't put the sample, but we have some sort of sample. We have a technique and an instrument, so something that we use, and something that we measure. It could be something that becomes colorful, something that releases heat, something that precipitates, and et cetera, et cetera. Now, the computational approach is not very different from that. So rather than having these techniques, you have methods. So you have the type of calculation, and your instrument is a computer or a supercomputing facility. The system response is basically the solution of equations. So basically it's numbers that then you post-process to derive properties, trajectories, reactivity, evolution of the system, or transitions, whatever you want to measure. It's very important to highlight that in the same way as when you investigate something from an experimental point of view, it's not that one technique gives you all the answers. If you want to measure electronic transitions and you have an infrared spectrometer, you won't be able to do that. In the same way, it's not that one calculation will give you all the answers. Depending on what you're studying, there are different techniques that you can apply that will give you different answers. So if you have a complex problem, you won't just be able to press a button and get an answer. So the advantage of this is that if it works and you do it correctly, you can basically see the atoms. So you can have a look at what happens at the atomic level. And you can do it at different levels. So you can, for example, quantify something that is not quantifiable experimentally. You can design. This is a big area, especially in pharmaceutical companies where they say it's called drug design. So they basically design molecules to test and try. It can be used to help interpreting experiments and also to make predictions. Now, in the context of mineral-fluid interfaces, so this is a sort of representation of what happens at one of these interfaces that I find particularly interesting. So you have a silicate, water and carbon dioxide, and a bunch of other stuff dissolved. And depending on the condition, you have the formation of organics. You have the formation of materials with particular structures and properties. Or you can have something that is becoming quite popular under the name of carbon dioxide geosequestration. Now, what modeling can help with is when you have such a complex problem, you can, for example, access one variable at a time. You can access extreme conditions, extreme temperatures, extreme pressures, extreme concentrations. You can actually simulate rare phases that maybe wouldn't last in an experiment. And you can actually access the fundamental science. And this is something that helps you build in the puzzle. So you won't find a model that describes everything, but if you have a complex problem like mineral growth of carbon dioxide geosequestration, you want to fraction it into puzzle pieces and go and try to contribute and find stuff around that helps you build in the puzzle. Now, the two main challenges with simulations. First is the accuracy versus time compromise. So these are 4 boxes. There are many more than this, but that's just a rough approximation of the kind of methods that you can have. This is the most accurate possible. And as you go up, you have less and less accurate. So here, for example, you have electrons. Here you have only atoms, and then electrons are approximated through a number of parameters. Then at some point you would have beads, and then you would go to continuum model. Now, why are we not running with the most accurate way? Because it's very expensive, like it takes a lot of time, the equations are very complex. You can access only small time and size scales. So this is for molecules, clusters. If you go up in size, then you have to compromise. And it's always a matter of finding a balance between what you want, what is feasible, and what you can do. The second challenge is the system complexity. So this is what it is in reality, more or less. I mean, it's more complicated than this. This is what you can do with simulation. So you can still do something meaningful, but you have to be aware of where you are and what variables you want to consider and what you can neglect. And that can be different depending on the property you want to analyze or the material or the process that you want to explore. So I'm working here at Curtin University upstairs in a group that we call ourselves Computational Materials Chemistry Group. And we do a lot of things, but most of what we do fits within these few points. So some of us are quite involved in method and model development. We work mostly with materials, but also with molecules and metal ligand complexes and stuff like that. Biomineralization and interaction with CO2-rich fluids, nucleation, dissolution, and more generally, everything that falls under material structure, composition, and properties. So not just mineral, mostly mineral, but not just minerals. And these are the people that are currently in the group. We never make it to take a picture all together. So we put the little faces. It's the 3, so Julian, probably a lot of people here would know Julian and Paolo and myself. And then we have 2 postdocs at the moment and 3 PhD students. and one is here. So Paul is there, Peter is there. Now, I will proceed with showing a few examples, trying not to be too technical. If it gets scary, just make some noise or toot and I stop. So this is vaterite. Now, vaterite is a rare mineral, and why should we care about rare minerals? So people have compared rare minerals to sporadic words in a text. I think it's a very good example. If you take the whole English literature, this is the words you're going to find more often. But it's the sporadic words that define authorship, the time, the content, and all of that. And in the same ways, rare minerals, because they are rare, contain a lot of information on the environment where they grew, on inspiring new materials or new synthetic routes. They can trace pollution, the presence of life, and other things. So vaterite is rare, but is it really rare? This is the question that people are asking themselves, because it's not very uncommon in marine life. And apparently, so these plants, so what you see on the leaves is vaterite. So it's very soluble. So every time it rains, it flushes away, and then it is regrowth by the plant, and it apparently helps capturing life. So it's a rare mineral, but it's not as rare, and it has strong connections with life. It's like the first mineral that a shell grows when it gets damaged, and it starts rebuilding the shell. Now, the problem with vaterite is that its structure, it's been a matter of debate for a few decades. And at some point, we ran some Raman spectroscopy study. This is the experimental spectrum. It looks like pretty much, it should look like you have the typical band you will find for the carbonates and all of that. But we said, okay, let's take all of the structures available, and whether they exist or not, we don't care. Let's simulate the Raman spectra. So we did it for each structure. We used a number of tools. For example, with simulation, if you want to see how much a peak is shifted by isotopic substitution, it's very simple. You just change the atomic number. So that's a lot more difficult to do experimentally. But with simulation, you can pretend like if every carbon is carbon-14, which are the peaks that shift, how much. And so that when you compare with an experimental sample, that can give you a lot of information. Now, with vaterite, that's a bit of a problem because they look all the same. So all the different structures give spectra that are pretty much the same, except if you look to specific bands, there are two that are different and that are the same as what you see in the experiment. So notably, these also correspond to the most stable structures. So through simulation and simulating Raman spectra, we could contribute to actually say this is the structure. And this structure is being confirmed, well, by Raman spectroscopy, NMR, X-ray diffraction, other experiments that consider other things. They work better if they assume that's the structure of the mineral. And now there are a bunch of papers that come out in Nature and stuff like that that keep saying that's the structure. So it's a popular topic, but yeah, basically we did solve the problem through simulation. So another example of application, so that one is just materials. There was no water, no interface. I give you a few examples of solid-fluid interface, and in the particular context of crystal growth. So the first example, these data are a bit outdated, so they're being revisited. Take them qualitatively, not quantitatively. But the purpose of this slide is just to show you how complex the fundamental science behind an ion pair forming is. So this is calcium phosphate, and this is the energy of formation, let's say the free energy profile of two ions that come together. So you don't have just two ions that come together, but you have ions that come together, get to a place where they are more or less stable at the distance they are, with water in between them. And then at some point, as water leaves, they get closer and more stable until they get to what we say contact ion pair. So this is, we call it solvent shared, because the two ions with the solvation shell, they share it. There's a solvent separated, and then they are fall apart. They're far apart. But this is just to give you an idea of how complex it is to develop a model that reproduces what happens in solution. You don't have to think about this if you do the experiment, because nature doesn't need directions. But when you do the calculations, if you don't tell the computer doesn't know. So you have to take account of these things. So another place where, so we go a little bit bigger. We move from ion pairs and we go to clusters. So quite in the past 20 years, the classical nucleation theory has been revisited. And the reason is because before it was thought to happen this way, which is probably what many of you have studied in back to the uni. So it's like you have ions that get together until they reach a critical a critical size of the nuclei, and then everything precipitates. So you have, if you look at the energy, the free energy of the process, you have one big activation barrier, let's say. However, it's been demonstrated that many minerals grow through an alternative mechanism that's made of what they call pre-nucleation clusters, and then amorphous phases that form, and then eventually you have the final crystal. And the profile is a lot more bumpy, but also the activation energy is a lot slower. So you have like the crystal growth that happens in step rather than happening all at once. And in particular with calcium carbonate, we were able to demonstrate, quantify, let's say, the structure and the stability of these pre-nucleation clusters that look a lot like polymer. This is calcium carbonate. The yellow dots represent the bicarbonate. And because of how they evolve in solution, they look a bit fluffy, they break, but they form again, so we decided to call it dollops, as for dynamically ordered liquid-like oxyanions polymers. And so these are just, there's no water, I removed the water, we removed the oxygen, so the yellow dots are bicarbonates, the blue dots is the carbonate, and green is calcium. So all the other atoms are present in the simulation, but not in the visualization, because otherwise you would just see an accident of atoms rather than seeing what happens. So this is, it's not the whole work, but this is just an example of the kinds of simulations that we've done and what kind of things we could do. We could simulate different pH, different concentrations, and then have a look at what these clusters are, their stability, and their structure. Now, third and last example I give about crystal growth, which is also the most challenging one, is understanding, which is the point of biomineralization, understanding the effect of organic additives on the formation of minerals. These are butterite, again, my favorite mineral. And depending on the chirality of the amino acid that you have in solution, they form left-handed or right-handed. And this is quite interesting. It's hard to understand why. Experimentally, they claim they see some homochiral clusters of calcium aspartate that form on the surface that direct this process. So we decided to explore these clusters and see what happens. So we started from an ion pair, and you see this is the typical profile that that is I shown you before for calcium phosphate. So we added an aspartate, we added the second one, then we added another calcium, and we did it in solution because we wanted to say whether this is something that forms in solution or if it's something that is a peculiarity of that surface. Now, these numbers, what all of them together tell you is that the association in solution is very weak. Just for comparison, if you have calcium and carbonate, this is around a little bit more than -20. So if you have calcium carbonate and aspartate in a solution, calcium aspartate will not form. It will go with carbonate. So the main conclusion of all of this is that whatever happens, it is a peculiarity of the surface. So we're still, this is still work in progress, but we are now bringing this further and analyzing what happens at the surface, because that doesn't depend on the solution itself. So just a little bit, how much time do I have?
Yeah, plenty of time.
Okay, good. So it's 6:30, 6:45, so I pause a little bit the hard science and I just give you a little bit of background on the history of this discipline, computational chemistry. Because sometimes when you know where you come from, you can understand why and where you are and what's the way forward. Now, chemistry is quite a young science, but the idea that we could calculate things coincides pretty much with the establishment of chemistry as a science. And it gave rise to many reactions. So some people say, well, that's absolute, that won't be chemistry. We can't calculate things, we're chemists. Whereas others were open to say, well, perhaps one day we will be able to calculate, to make calculations about chemistry. Now, guess who was right? Now, in the first 30 years of the 20th century, all of these people, plus a few others, figured out everything. So by the 1930s, we basically knew everything about the matter. But the equations, which were correct, but were too difficult to be solved. So we knew everything. we knew everything, but we didn't know how to solve the problems. So since then, a lot of efforts have been put into developing approximations and algorithms to solve what can't be solved with pen and paper. And this coincided also with the rapid evolution of computing facilities and computing powers. So I have to stress men and women because, so this was my professor back in Turin. And when in late 60s or early 70s, she was offered a contract in the US and for 1 year to do this work. And because she already had a position in Italy, she said, I can come, but just for 6 months, otherwise they will cancel my contract. And what they told her in the US is like, we have very little expectations from Italians, and even lower if it's a woman. So just come and do whatever you can. So she said, well, I'd better be doing something. So in 6 months, she delivered what was supposed to be a 1-year job. This thing got published and was a reference for many years. But when it got to the publisher said, saw the name Carla and said, well, no, this is no job for a woman. So that got published as Carlo Roetti. So now it's corrected on the online version. But this is, so yes, Carlo Roetti, because they didn't, they guessed that there was a typo in the name because it couldn't be a woman. So things have changed a lot since then. This project has been discontinued, but the website is still on. And it's a collection of all the women in computational and material, in theoretical and computational chemistry, material science, biochemistry. So whenever there's a conference and you have male-only speakers and they say, well, there's no women, and then people point them at this website. Now, I've mentioned the growth of computing power. So the data stop here because this was a personal communication to one of my professors at uni and in the early 2000s. So I don't have data after 1998, but it's probably something you can run on your phone in a matter of seconds. So these were computers in the army. So this was the most advanced technology you had at the time for calculating the energy of these molecules. So clearly they didn't do it here. Maybe they've done it here. But yeah, now it's something, it takes a matter of seconds. But how did supercomputer look back then? They looked like this. And surprisingly, even if computational sciences are not particularly popular nowadays for women, the vast majority of technicians and people that were working in there, maybe not the vast majority, but a lot, were women. And you probably have seen the picture of Margaret Hamilton with the code that brought us to the moon. But there were many Margaret Hamiltons. And just before going to next, what you see here, so the components are so big that a bug could actually be like a spider or a moth or even a small mouse. And so one of these outstanding women was Admiral Grace Murray Hopper, who did a lot of amazing things, but she's became very popular because she actually found a bug. Like there is a logbook in a museum in the US with a moth sticked and it's a first actual case of bug being found, and after then the term became very popular. And this is how these facilities look today. After all, they're not as different. I mean, they're pretty much the same, but look a bit fancy and with smaller components. This is in the US. It used to be in the top 5. Now it's about I think in the top 10. But the reason why I choose that one is because there is this nice visual that they developed, and it's like, just to give you a feeling of the power, is if every person on Earth completed one calculation per second without ever going to sleep, so continuously for 305 days, you would do what this computer does in 1 second. So it's, and what do we use this computing power for? Pretty much everything, from simulating the flow of a crowd out of a building in an emergency, to finances, supporting health, experiment, weather forecast, computational chemistry. So this is, we usually classify the humankind eras based on the material that has characterized that era. And many people say we're living in the silicon era, so it's in the age of information. And so what to expect? I find this quote from the former CTO of Cisco particularly meaningful. So it's not that machines are going to replace chemists, but chemists that can use machines are going to replace those who don't. And I think this is pretty much valid for any discipline. Indeed, in the field, so this is not my area, but there's an emerging area, and there are universities around the world that have masters in this, that is called digital chemistry, which is the application of artificial intelligence, machine learning, deep learning, to every aspect of chemistry, including customer service. So not just computational chemistry is my area, but there's a huge emerging area within the chemistry discipline to support every aspect of chemistry, which is based on computers. So I would expect in the next maybe 10, 15 years, this is something that the future chemistry graduates, it's a skill that will be a requirement. Now, the future ahead, I don't have the crystal ball, but what I can see in the near future for computational chemistry, not for the whole chemistry, is we will need, so we have these amazing hardware capabilities. They are evolving a lot faster than the speed at which we can write codes, at least in computational chemistry. So we will need to be able to exploit this increasing capability, add more complexity to models. So, well, I didn't go through that in the specific, but there are some limitations in every technique. So it's about going beyond those limitations. And also another emerging area, which is the one linked to machine learning and all of that, is data-driven materials chemistry. Now, about myself, my research in computational chemistry is not the only thing I've done in the past few years. I've been quite involved at a national level to advocate for the future of research and researchers, because research is made by people. If you want people highly skilled and honest to do research, you have to make sure that the environment where you do research is a welcoming environment, otherwise they won't do it. So I did spend a considerable amount of time volunteering at the Australian Academy of Science with the EMCR Forum, working with the Academy, with ASC, government on these topics. And also I've worked with ACOLA and the Office of the Chief Scientist on understanding whether the way we assess research is the right way to assess research, and how does the way we assess research influence research. Like, we are all about H-index and numbers. So if I want to engage in a field that is challenging but doesn't give me any easy publication, I'm a lot less likely to undertake that research, because I'm going to die as a researcher, because they won't fund me, they won't hire me. So is this what we want from research? There's an interesting paper published last year which measures the amount of papers and patents and everything over time, which is increased. But then they measure how disruptive those papers were. So how much they break with the science of the past and bring innovation. So if you look at the plot, the amount of innovation per year goes this way, and the amount of paper and patents goes this way. So it's like we're wasting, with this method, this way of assessing research that we're having at the moment, how much we're wasting, how much we could do if we assessed research differently. So I don't have a solution, but I think during my service here, I pointed out all the problems. So, and it's good because sometimes you talk to these high-profile people and you say something that is obvious from an early career, mid-career point of view, and they're like, oh, really? I never thought about that. Well, that is. So, so I think it's an important area, and so I encourage all of you to engage with this space if you have the opportunity to. And I'm done.